planes, which is lines. So we just look at lines and how well we can approximate. And then the theorem in this case states the following, so that if we take the points, so we have an image here, which I should put, I can see her there. So here's what we're starting with, okay? And now we have a theorem which says the following. We're going to compute the following. So for each data point x here, we'll look at the squares that contain it on the various scales. And now we will sum these numbers, which you should think of as between 0 and 1, over all scales, or over a large number of scales. And let us assume that we fix a number a. So the number a is at our disposal. And what we do here is we start and we just numerically compute the various values. No, you do it for every point. You take every single data point and you do this. So you have to have quite an effective algorithm in order to be able to do this for each point. And I've lost the picture of the histogram. Well, so you do this for every point. So first of all, you better have an n log n type algorithm, or you can't do anything. But there is a nice n log n algorithm for this. And if you're in the following situation, so let me rewrite it this way. If this happens for a set, so we're given a probability measure here. For x in some set E with measure of E equals some number delta, so you should think of this something between 0 and 1. Then a large piece of this set is rectifiable or described by one-dimensional data extremely well. So then there exists a curve gamma with two properties. So first, its length is bounded by e to the universal constant times a. And second, this curve picks up a lot of the measure. And how much measure does it pick up? It picks up at least this fraction delta times e to the minus constant a. Now, so that's the theorem, and what does it have to do with the picture? What it has to do with is the unreasonable effectiveness of the algorithm. So that what you're doing here is you do this calculation, and then there's an automated way to pick this number a.
Are you doing the following? Are you now using that curve to draw the thing, say, in this bottom left corner?
No, but there is a curve. So what the theorem says in this case is that the bottom left-hand picture has associated to it a curve, which you might think of as a parameterization if you want that psychological crutch. This curve goes around like this. How long is it? It is this length. That's the length.
Is that used to draw that or not?
No, it is not used to draw it.
The points in K naught are which axes? Are the axes for which this beta?
So they are exactly the x's for which this sum is small. And then I have
The other ones are the ones for which it's large?
and the other ones are the ones for which it's large, and the picture is simply the union of these two. So
the A varies from picture to picture, basically. What is the A? What is the A?
So here what I did, so this is a good question because this is like a microscope. You have a picture and you get to focus in at various places. Well, so here's what I did in this particular picture. You have infinite number of choices how you pick A. In this particular picture, what we did was we looked at the maximum value of this sum. So we get little m is the maximum value, and then there's, minimum value, then there's a maximum value of this, which you just compute, and you divide by 2, and this, in this picture, was arbitrarily the number A that was picked. That's completely arbitrary. Okay? And so what happens, now you see in many cases you don't care about this curve. You just want to know how one-dimensional is it. And this theorem tells you that there's a theorem. Now, there's more to this theorem. This theorem tells you exactly how this parameterization is built if you want to build it. And it tells you where, you see there's this funny looking estimate that you're not left with very much. It tells you exactly how that measure is shed and put into this picture. And it turns out that there's essentially only one way to shed, and you understand how the two fit together this way. But I'm not sure I've ended answering your question.
No, I still don't quite understand how you use gamma. I mean, what exactly is it? Or let's say the algorithm.
It does not appear. It does not appear. The theorem is not used to produce the picture. Yes. 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 The statement of the theorem about the picture is the following: that this has a large piece which is contained in a curve of small length. In fact, as it turns out, because this picture comes from a definite physical object, what actually you get for the estimate is there is a parameterization of the entire set here of small length.
By iterating this.
No, there's something funny here. There's something peculiar. So you expect that you can iterate and get full measure. This actually turns out to be wrong.
Well, you get several curves.
But you get no estimate. It turns out there is simply no legal estimate except this one, even after iterating. However, this is still the correct statement, because if you take data that comes from any kind of physical object, this bad mathematical estimate, this is a mathematical theorem, it turns out not to happen with actual data sets. And exactly what Alain is saying occurs, that there is an iterative procedure. You get to add pieces and you recover through this. This particular image has the property that you don't have to do that iterative procedure. It happens all at once. Yes?
Peter, I heard talks by various people doing image processing, and I could never quite pull together what they are trying to do. So what is the goal of this particular decomposition? So what do you do once you get these sort of partial pictures?
So first, I'm out of my own country, so I'm allowed to say things I'm not allowed to say in the United States. This is sort of like the old question, what do women want? Right? So having made this highly controversial statement, Rafi, why don't you enter the fray right here and talk about this?
The real challenge, the real problem in the real world is this. Consider the example of, say, 30 million fingerprints would sit in the archives of the FBI. We know that 15 parameters are sufficient to identify each individual person. So this collection of points in 250,000 dimensional space is parameterized by just 15 parameters, and over the last 120 years, people have empirically built this parameterization. The question is really, can one come up with a systematic method to analyze fitting in this view? So a contained parameterization, which is by the, in other words, the parameterization, which is the property that in parameter space, the distance disrupts the distance in embedded space. Okay, so that you then parameterize the space and identify a person by its spatial coordinates. It doesn't have to be 15, it's very likely that in some region of fingerprint space, 3 parameters are enough, and in some region, 9 parameters. And so the question is, first of all, and it's not clear that there are several challenges. It's not clear that it can be done, but the incredible thing about the serum that we've seen here is that just by doing local L2 deviations, or statistics essentially, from low-dimensional planes, you have a way of deciding whether a global or semi-global parameterization actually exists and synthesize from that. You're doing metric statistics locally. I mean, like the traveling salesman, you were just looking at how much the collection of points deviates from the line segment. But just measuring this, and it tells you, well, there has to be a curve whose length is estimated by the local variations that you have computed, which are the beta numbers.
What was the question to which that was the answer?
No, why one does it? So the question is,
No, but his question was not why did you do that. His question involves some word image. What?
well, I'm referring to image. I'm giving you an image.
I mean, this is an example of an image processing algorithm, and I wanted to ask a bit of putting it in context.
Do you have Mandrill here? So let's put this. So let's talk about Mandrill.
I would like to know
But I want to look at the Mandrill.
I mean, there's stuff, the edges here are stuff that you can do with the Mandrill. On the other hand, here is really one-dimensional parameterization, two-dimensional parameterization.
Oops, wrong one.
So let's say, although I know this is idealized, but suppose that this were the best possible algorithm, the solution things. So what you would do is that you run this tree to some depth, and then that would identify
The one-dimensional region.
That's right.
the fingerprints.
Yeah, no, for an image, you will not do it as an image. You really do it in 250,000 dimensional space. For fingerprints, if the issue is to identify, you will not do it the way it's done here.
So for example, I know you don't want to talk about it, but I do. Okay, so if we look at this picture, well, as an image processor, you might just look at the picture and say, this is a function. So at each pixel, you have some defined value. But then to understand the global structure, you can do the following. You can say, I'm not just going to look at the pixel. I'm going to look at its neighboring 8 pixels. And now the function I'm looking at is not a real valued function. It lies in 9-dimensional space. And now I can repeat this and build up huge dimensional space. How do these vectors fit together? All right, so if you land in an area where this vector valued function now doesn't vary much, say it's linear, then you have arrived in an area where you have some sort of effective description with a low number of parameters. And that's a realistic type of problem that one would look at. So let me just comment that that there's this highly abused place where people try to do image processing, which is on the top picture. But you can view it, I mean, you can view it as a problem in image processing. You can. There are any number of boxes you can put this problem in. But, of course, the central problem is how many parameters do you effectively need to describe this? Is it one-dimensional? Is it two-dimensional? And where is it so? Same kind of problem. Yes.
The theorem seems somewhat reminiscent of the decomposition of one sets into accountable union rectifiable curves and irregular ones. So is there some close connection?
Yes, so this is, in fact, I thank you for raising this because it's all based upon the Besakovich theory. So there's a Besakovich theory of d-dimensional sets where d is an integer. And then what the game here is the following. You have a set, it lies in Rn, you have a dimension d, and the technical condition is that the Hausdorff measure is positive but finite of this set. So, and then you want to decompose this set into two pieces. Roughly speaking, the regular piece, according to Besakovich, is the place where you can describe it by C1 graphs or Lipschitz graphs. And technically, this piece is a countable union of subsets of Lipschitz graphs. And then the other piece is some bad place. Or a good place, depending upon your terminology, where there are no tangent planes in any reasonable metric sense. And there's this canonical decomposition. There are theorems telling you that the irregular piece projects very poorly. In almost every direction, you see nothing when you project. Whereas for the regular piece, you can project it and see it in certain directions. Now, one of the central points of this theory was exactly to build an effective version of the Besakovich theorem, which has been done, and I hid here. So it's exactly what I referred to earlier as an effective version of Sard's theorem. So it is exactly that.
That's where you need C1 plus, that's a lot in the discussion. You said there was no C1 theory. This is a C1 theory.
This is a C1 theory.
Right, but you don't have the estimate without the epsilon.
Oh, no, you have an estimate, but you have a different kind of estimate. So the point is, the C1 plus epsilon theory gives you estimates about what happens when you project. So we have to give those up because they're in the C1 category, all sorts of counterexamples, trivial counterexamples exist. But what happens is that you get these quantifiers like this, that they're nice low-dimensional subspaces of a quantifiable size. That is exactly the point. Yes?
You used the word effective. Does that mean that you can really construct this gamma? For instance, you're picking
Yes.
LD now. Could you reprogram the computer to
Yes.
a single curve that creates a calculable thing?
Yes, and let me describe exactly how...
You said you didn't do that, but you were asked to, or you could do it.
Yeah, that's right. So the reason I didn't do it is that in certain cases you don't want to. But suppose you do want to, right? Because so this is my comment before. Why do you want to write a parameterization? The parameterization may be more complicated than the set. However, it's very reasonable to do it and ask, how is this done?
Little kids are often asked to trace a picture.
Yeah, exactly. And they will discover that it's much easier. If you do connect the dots, it's obviously easier to do it here than here. Okay? How is this done? It is done exactly by the following mechanism. And this program keeps exact track of this algorithm. It's stored in there, and I've just thrown it out for purposes of presentation. So it first looks at this scale and says, can I approximate it by a line? And you look around and it says, no, not really. I don't know what to do. So it chops it into 4 pieces. So you just go like this. Now all of a sudden in the bottom piece, you have something that looks like a good line. And up here, you definitely see a nice line, etc. And over here, actually, this is statistically a good line. There's some problem over in this box, so we delay this for later. Now what do we do? How does the algorithm for parameterization work? You take these 4 lines, this one which is well-defined, that one which is well-defined, this one which is well-defined. Now this one, you just take another boundary of box, and you fit together those 4 lines. Now you have three line segments plus the boundary of a box, and that's your initial approximation. And now it just iterates this. It just keeps track of where. So here, let's just look at the bottom fourth here.
You have to pick a direction to go around, or
Yeah.
curve bifurcate. There's a real curve, it's parameterized.
It's a real curve, so if you want to parameterize it, it's an elementary problem in graph theory. Once you build the connected set, you can parameterize it. So that's easy, actually. It's much harder. There's definitely a technical problem in terms of parameterization when you talk about two-dimensional surfaces. But here, the parameterization is quite simple. And you start with an initial desire, which is, say, to start from here. You could pick any possibility. And then as this multi-scale algorithm goes through, it will keep that parameterization but refine it to the various scales.
So, I mean, if you go in these trees, so you're going to label the case 0, 1, 1, etc.
If you go,
You will have
yes,
case 0, K1, and case 0, 0, K0, 1.
exactly. So we get
The distance to the first 0, when you use this here, it will give you, will be the double exponential, the length will be double exponential in the distance to I guess, the first 0.
yes.
Each time you go down, A can possibly go up by a factor of 2.
Well, let's see. So let's look. So you see here, we have a certain value of A. Now it never goes up in the next two pictures. Here it goes down.
No, but if you go on the right side,
But if you go on the right side, yes. Here it's gone up. It's gone way up, and then over on this picture, it's gone down from here, and it's
if
still
you remove the last one, it will be double exponentially the length of the tree.
exactly. Exactly. Yes.
I have a question for Rafi. Rafi mentioned that this point of view of moving orthogonal system have application in mathematics. Can you say something about it? In classical mathematical programming?
Yeah, what I was basically alluding to is the fact that people who do harmonic analysis or study the behavior of partial differential operators usually do something called micro-optimization, in which you look at the frequency content, say, of the solution to a differential equation in a given region in space. You localize in space, and then you look in the frequency domain, what are the main contributions. So this is a standard tool that has been around for a long time, but it's always done manually. In other words, you look at it, you try to understand the geometry, how things interact, and so on. The question I was posing is how to automate that particular procedure in the case that you actually, say, doing a computation of the model and want to represent a solution. This is what would happen if you take some complicated nonlinear evolution equation that you don't really understand initially. Then what you want to do is, at each time step, understand how you should segment your spatial coordinates and the frequency coordinates at the same time. And that would be variable from one point to another.
So there's also application for computing.
Right. So let me give an
There was some pure application of these ideas, actually for classical problems, some harmonic analysis. It does not involve computing.
Yeah, sure, of course. I mean, it goes from just the basic understanding, for example, on Carlson's proof of almost everywhere convergence of Fourier series. You realize that when you track down the proof, what you're really doing is this sort of decomposition in a much more subtle way, and you can reorganize the proof to give a somewhat simpler conceptual way of providing that proof. Another question, which has been an open problem for, I would say, 30 years, involves the bilinear Hilbert transform, which needed to be, in order for that to come about, there was a need to have, first of all, you could get a very simple model by using, say, Walsh-type situations, and then organization work was quite obvious, and how to do the combinatorics. And then that gave a guide to actually prove the theorem that was open since 1965. I would say.
It's image processing in the phase space, basically.
Everything was done in the phase space, right. Right. Image processing in the phase space. It's exactly that. It's exactly what happened. And it's rather clear that this is I mean, there are lots of other classical things, like you could take expansions in spherical harmonics on the usual sphere, and you want to get a fast way of computing it, or you just want to understand what really the expansion looks like. And then you find out that it's really a lot of little Fourier series sort of spread around, but it depends on where you are located on the sphere, what range of degrees of harmonics you are at, and so on. And so it's a complete decomposition in the phase plane. Again, in the same spirit that what happened to the magnet. It's exactly the same thing. So this is, I mean, in some sense, it's all the new at the same time. The new is the tasks you want to assign to it, all the sort of traditional harmonic and operator.
Actually, you have this in graph here also. You try to describe graphs, whatever, playing around with the structure locally of the graph, and then the structure when you try to expand it in the world.
What do you mean by graphs?
What do you mean?
Functions or what?
Well, on one hand you have the graph like it appears, and then on the other hand you can look at its expansion in the world series, where the graph is seen as a big indicator function of the temporal graph. So there is this kind of general respect to these local properties from the expansion of what's that? Like what happens in thresholds.
But actually, I was alluding really, and for some reason it didn't come about. There are classical formulas in complex function theory having to do with factorization of holomorphic function using Blaster properties that are very unpleasant formulas, and you don't really understand what they're doing. And it's very easy to see that those formulas provide you a musical script, a score of the functions that you have factored. If you're interested, I'll show you some. It's absolutely magnificent. It explains all the parameters in the formula in a beautiful way. You just read it as music.
To what extent do you understand which instances these methods work for and which instances they fail on? Do you have any understanding of, what Rafi was describing or what you were describing?
I think the honest answer is no, because at this point one is looking at rather simple objects where one already has some sort of understanding. For example, this picture over here is created by Fourier analytic methods, so it's a cheat in some sense. And if you look at let me just say the financial data, you do have some rough understanding here of what you're looking for. But one way to express this problem is how many pictures are there? I don't think we know if it's so. So it was asked yesterday, are there 4 or 30 or 300? So we seem to know that there's certainly not just 4. And the guess is somewhere between 30 and 300. And I don't think we have a very good picture of these. One of the reasons is that we don't have effective ways of describing the interesting pictures which happen in very high dimensions.
So I don't know, to what extent you are familiar with this work that's being done on this. The very general question that Rafi raised, which I think is a scientific question of the highest order, you have some, low-dimensional structure like the FBI files or a protein describing some function of the galaxies, and you want to extract, and it's given in a very high-dimensional space, and you are just trying to extract the essential features. Of course, this is people in vision work on it. Of course, people in all these areas work on it, and you want to do it automatically. And I think one question, the reason I asked about if you understand the types of instances for which it works and instances for which it doesn't, is to describe this kind of, have a mathematical formulation of the distributions under which a particular algorithm would work, and more generally to describe algorithms, even heuristics, that whose qualitative behavior, whose how well they'll do, depend on some essential intrinsic parameters of the problem, of the data set, or of the distribution of data sets.
Mm-hmm.
And there are some very general methods that were developed, for example, by Tali Tishby in the Hebrew University, in which it will give, pictures like this, or will give, extract from the financial data something much more meaningful and low-dimensional than originally, that depend on some information content of the description. So it's done in a different way, and not via a fixed representation, let's say a particular Fourier decomposition or some kind of recursive structure. It does not tell you initially which representation you like. It's more like solving a very complex optimization problem in which you are trying to condense the information and form it to extract such a representation.
So if I could try to give two answers, one a kind of negative one. I think it's quite clear that there are a lot of different approaches. It's not clear a priori which one is best, and I wouldn't claim that one absolutely is the one that one has to do. And I mean, we see a long history of this, for example, in image processing. On the other hand, I think there are some good positive hints that from knowledge of certain dynamical systems, we now see that certain structures tend to be canonically embedded if these come from particularly physical processes, and these are in fact quite well described in the cases that we know by methods of this type. Stronger than that, I would not say.
Okay, thank you.
Let me answer that.
I think that the time is
we can talk about it.
so I think that you can continue with the time. Thank you very much.